Welcome to this final video on gravity. We'll be talking about field lines, center of mass, some calculus, and we'll finish off with a recap of everything that we have done. I hope that you will enjoy. So what will you learn today? You will learn how to sketch field lines and equipotential lines near Earth's surface. You will learn more about center of mass and how it is properly defined. You will learn how integration and differentiation relates force and potential energy. And we'll end with doing a recap of what we've been doing in this series. Field and equipotential lines. We'll be looking at these near Earth's surface. You already know how Earth's gravitational field near Earth's surface is acting downwards, because objects accelerate downwards because of Earth's gravity. And we can illustrate this by drawing a set of lines, called field lines, acting downwards. We can also draw a set of horizontal lines called equipotential lines, which just illustrate that when moving along these lines, an object has unchanged potential energy. So for example, if we lift this object up, since we're working against the field lines, it will gain potential energy. If we then move it a bit to the right, there is no change in potential energy because it's moving along the equipotential line. And then lastly, if we move the object downwards, it's moving along the field lines, so it's losing gravitational potential energy. We will now revisit the concept of center of mass, and the single most important thing that you need to remember about center of mass is that gravity always acts on the center of mass. Sometimes in books, they might call it center of mass or center of gravity. I'm calling it center of mass, but they essentially mean exactly the same thing. So an example, you're balancing a wooden plank on your finger with two 10-kilogram weights on either side. We know that the center of mass will be exactly in the middle because the weights on either side are balanced. And since force due to gravity acts downwards, it's acting straight down on your finger, so this is a stable configuration that we have. Here we have moved one of the weights slightly inwards, and this will actually move the center of mass in the same direction. And since gravity acts on the center of mass, this will cause the plank to rotate, so this is an unstable setup. Similarly, if we would have a 5 kilogram on the right side, this would also cause the center of mass to move inwards. And since gravity acts on center of mass, this is also an unstable configuration. It's according to these principles that one of the following setups that you might have seen works. The center of mass is actually on the white dot indicated on the bottle. And since force due to gravity acts on that dot straight downwards, that's where it will balance on the pivot. Earth's center of mass is extremely close to Earth's geographical center. And it is for this reason that we always measure distances where gravity acts relative to the radius of the Earth, because they are so close that they're essentially equivalent. Now over to something really interesting, which is calculus. Some of you might be familiar with calculus since earlier, and some might not, but I'll try to give an intuitive understanding of how we use it here. You will recall how the area under this force-distance graph is the work done in taking James from the radius of the Earth's surface, to our James, which is where he is now. But how do we calculate this area under the curve exactly? Well, we can approximate it by dividing up the area into rectangles. And we know the formula for the area of a rectangle is just height times base. The height in this case is the force due to gravity evaluated at each point, and the base we will just call delta r, the same for all rectangles. So, substituting in the values that we have, we get this. How do we make this approximation even more precise? Well, we divide it into even smaller increments, more rectangles to sum up, and a smaller delta r. And in the limit of infinitesimally small increments, we write that delta r becomes dr, and the sum becomes an integral. So the total area approximation that we have becomes an integral. So in general what we have is that the change in gravitational potential energy is the integral of the gravitational force with respect to distance. Now if we let James fall back from infinity down to some final radius rf, we can evaluate this integral and his change in potential energy. So we have this integral with the limits rf, his final position, and infinity, his initial position. We can pull the constants out front and do the integral on r to the minus 2, and what we end up with is this. As we've seen before, the second term is equal to 0 because we're dividing by infinity. So what we end up with is negative gmm over Rf, which you might recognize as the definition of gravitational potential energy. That's the end of new topics to cover in this video, and you should now know how to sketch field lines and equipotential lines near Earth's surface. You should now know more about the center of mass and how it is defined. You should know how integration relates force and potential energy, and we'll come to the differentiation part later in this video. Now it's time for a recap. In the very first video, we went over how the force due to gravity near Earth's surface is called weight, and it's given by mass times gravitational field strength. Weight is given in newtons, mass in kilograms, and gravitational field strength in meters per second squared, same units as acceleration. Important to remember is that weight is a force in newtons, it's not given in kilograms, and it acts from the center of mass of the object. G is the gravitational field strength, and it's independent of object mass, but it varies depending on planet mass and radius. On Earth's surface, the gravitational field strength is equal to 9.81 meters per second squared. We talked about weightlessness, and how when James is standing still on his scale, the two forces, the normal force from the scale and his weight, exactly balance, and the apparent weight is equal to James's real weight. But when the elevator cable snaps, there is no normal force anymore because the scale accelerates with James towards Earth's center, so the apparent weight is 0 newtons. In the second video, we went over Newton's universal law of gravitation, where we have force in newtons, the gravitational constant, the mass of the planet and the mass of the object, both given in kilograms, and the separation between the two in meters. The negative sign is there to remind you that the force is always attractive, and the r squared term makes the law called an inverse square law. Again, the gravitational force is always attractive, and both objects involved experience equal and opposite forces. The force due to gravity acts between the centers of mass, and they can be considered as point masses. The sizes of the object don't matter. We can use Newton's universal law to calculate the gravitational field strength of other planets. Starting from the law, we can separate out the mass of the object, ending up with an expression for the gravitational field strength, which we can use to calculate G for the Earth, or for Jupiter, or for a football. We then explain gravitational potential energy near Earth's surface by considering the work done on lifting an object. So if we lift this weight 2 meters up in the air, we can consider the work done on it, which is the force times the distance. So the distance in this case is 2 meters, the force is mg. So we end up with mg delta h. So near Earth's surface, the change in gravitational potential energy is equal to mg delta h. Now in space, we have a more general expression, which is negative gmm over r. The change in gravitational potential energy, just like near Earth's surface, we can calculate by considering the final energy minus the initial energy. Important is that only a gravitationally unbound object has a gravitational potential energy of 0. Gravitational potential energy is always less than or equal to 0. All bound objects, for example on Earth, have a negative gravitational potential energy. They require positive work to become free. After considering James's change in gravitational potential energy in taking him from the surface of Earth up to some higher radius, r James, we then considered what happens when we take him from the surface to a distance of infinity. We tackled this question by considering the area under the FD graph. And we calculated this area using the change in GPE is equal to the final minus the initial. The final in this case is 0 because we're dividing by infinity, so we end up with an expression gmm over r Earth, and this is the work required to free James from Earth's potential. We then use this result to tackle the question, how much initial velocity must we give James to make him just escape Earth's potential, if he's standing on Earth's surface? So we know that the work required to free James from Earth's potential is equal to gmm over the radius of Earth. And we set this equal to kinetic energy. So when we have this, we solve for v. And what we get is an expression v equals the square root of 2gm over r Earth, where m is the mass of the Earth. So we see that the escape velocity, the velocity that we need to give James in order for him to completely escape Earth's gravitational field, this is independent on James's mass. For Earth, the escape velocity is equal to 11,186 meters per second, an enormous number. We'll finish off with a summary of important quantities we have encountered and how they are related. We will start with quantities that are dependent on object mass. We have the force due to gravity, minus gmm over r squared. And we also have gravitational potential energy, minus gmm over r. Force is given in newtons and energy is given in joules, and we can get from force to energy by integrating, as we saw in this video. The mathematical opposite of integrating is differentiating, so we can get the other way as well. Now, properties that are independent of object mass. We have gravitational field strength given in newtons per kilogram, which is the same units as acceleration. And on the energy side, we have what's called gravitational potential, given in joules per kilogram. Notice how in both of these properties, the object mass is not present. In much the same way as above, we can get in between these two by integrating and differentiating. That's the end of this final video in my mini-series about gravity, and hopefully you found these videos helpful and enjoyable. If you have any questions, as always, just put a comment below and I'll try and respond, or just save your question and ask me on Wednesday. I'll see you soon.